Morning guys, today we're going to go over 10.1. We're not going to give any more subjects and vectors, and you can expect an exam this Thursday or Friday maybe or maybe next week on vectors. We'll talk throughout the week. Now today we're going to go over 10.1, sequences and series. It's a very important subject. Besides this subject, we're only going to look at limits and derivatives, and that's it for this year. We'll also have a project to work on later on. But sequences and series, it starts off pretty straightforward. So what is a sequence? A sequence is just a group of numbers that has a particular order. Sometimes you can look at the sequence and just know what's happening. They're just in chronological order. You can have a sequence that's only even numbers, etc., etc. You can have different sequences. There are some sequences that have shown up in very famous movies, like, the Fibonacci sequence. If you look at certain Dan Brown films, etc., etc., the Da Vinci Code. There's a lot of sequences in our life that you can just see everywhere, pretty much. So these are some key words that you do need to know. So we went over sequence. A sequence is a group, the actual definition of the book is just an ordered list of numbers. So a group of numbers that follows a particular order, etc., etc. Just make sure the word order is included in the definition. Now, term is what we call every single number in that list. And the terms can be listed using this notation, a to the nth term. So this would be the first term, this would be the second term, this would be the third term. Note that this does not represent the actual number. So the first term could be 5, the second term could be 10, the third term could be 15. And just by looking at this pattern, you can definitely see that the fourth term would be 20 because it increases by 5 every time. Now, these sequences can be finite when I have a particular list of numbers. I have a beginning and an end, or infinite when you see this. That just means that the domain of that particular sequence just goes on forever, does not end. And lastly, formulas. We'll see later in example 2 that they can give you a particular formula for you to find the next number in the sequence, or the next 3 or 4 numbers. Now let's begin with example 1 in the book. Today we're only going to go over examples 1 and 2. In examples 1, I have A, B, and C. And it just says pretty much find terms of sequences. Let's look at the first one. Example A, they're telling me the following sequence: 2, 7, 12, 17, infinite. And they're asking me, just find the next 4 terms. Again, you'll see there are some tricks to find these patterns, but the first one is just straight up observation. Am I looking at even numbers, odd numbers? Adding sequential values to certain numbers. So there's a whole bunch of different ways we can, dividing, multiplying by a particular factor. There's a whole bunch of things that can happen. So let's just observe and try to just crack the code. Here you can clearly see that each number is increasing by 5. So just by observation, I know the following term will be 22, 27, 32, 37, etc., etc. That's pretty much it, just, basic observation. See if you can pinpoint the particular sequence the numbers are in. Example B, again, it's somewhat trickier to just observe, but you can see that they give us the first way to kind of like, as a formulaic manner, just to try to crack the code, so to speak. Now here it's not as clear, I'm not adding a particular number because the values are increasing. I'm definitely not multiplying by 2.5 because it doesn't make any sense here. So one way you can start to find the actual sequence is to subtract the following number, or to subtract a number from the following number. So let's try to subtract the first term, the second term minus the first term, 5 minus 2. Let's subtract the third term minus the second term, 10 minus 5. And let's continue. And let's see what happens. Here, the answer is 3. Here, the answer is 5. Here, the answer is 7. Now, if you can visualize the differences, there is a particular sequence, 3, 5, 7. What number would be next here? Probably 9 and then 11. So what I'm doing is I'm adding a sequence of odd numbers to a particular value. So 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 7 is 17. 17 plus 9 is 26. 26 plus the following odd number, 11, is 37. 37 plus the following odd number is 50, and so on and so forth. So I can see that there is an actual pattern which is easily visible in the differences. And actually, yeah, I did it correctly. 3, 5, 7, 9, 11, 13, etc., etc. Now, let's look at the third example where they're actually giving me a formula and they're telling me find the following values. So if we copy the formula they're giving me, it's pretty much the following. AN, remember N stands for nth term, first term, second term, third term, fourth term. I'm just gonna plug it in for my N or substitute. 2n negative 1 to the nth power. And they're telling me to find the following values for f of n, pretty much, or actually, for n equals 1, 2, 3, and 4. All we gotta do when they give you the formula is substitute. And one thing to keep in mind, don't confuse the C from this page with the following example. Because the following example, they're giving you a more complex formula with different rules, and they're asking you find, the following values. Here, they're giving you the formula, and they're telling you, plug in these numbers and tell me what the answer is. So again, the first term of that sequence, all I gotta do is plug in my n for 1, follow proper PEMDAS. Negative 1 to the first power is negative 1 times 1 is negative 1 times 2. So the first term of the sequence is negative 2. Let's go over the second term. I plug now a 2 in n. And remember, that's the pattern. Even though it might jump from negatives to positives, it's not always going to be, it's in increasing order. That's the formula you're given for this particular sequence. Okay, so negative 1 squared is 1, times 2 is 2, times 2 is 4. Third term, negative 1 cubed is negative 1, times 3 is negative 3, times 2, negative 6. Fourth term, I'm going to substitute again my n's for 4. This becomes positive 1, 4, 8. So you can see that the sequence is negative 2, 4, negative 6, 8. It increases by 2 and the signs flip. So if I had to guess, the next value would be negative 10, then positive 12, then negative 14, then positive 16. So you can see some patterns are trickier than others. Again, here it's kind of easy to visualize because they gave you the answer, but it's not that simple sometimes. So that would be example 1, part C. Now we're going to go into example 2, which is usually what you will be doing in tests and SATs and math tests, etc., etc. Now, example 2, it's called recursive defined sequences. And now, if you know programming, a recursion is pretty much that you use a value, you plug it in, it gives you a new value, then you take that new value, you plug it in again, it gives you a new value, and you plug it in as many times as you need. So it's like a circle. So let's say I begin with a 1, I plug it into the equation, it gives me a 3, I plug that 3 in, it gives me a 5, I plug that 5 in, it gives me a 7. That's recursion. Okay, you use the new answer in the exact same process to get a newer answer, and then you use that newer answer, plug it in to find an even newer answer, and so on and so forth. So again, let's look at the rules that are given, because again, recursion, they give you very particular rules. So they say, first of all, that A1, the first term, is 1. And that's incredibly important. That's the first value I'm going to plug into my system. It could be a different number, but in this case, the first term is 1. They're also giving me the formula. The formula pretty much states that A to the nth element equals A n minus 1. Let's just put it even smaller. N minus 1 plus 2n minus 1. And they're also giving me a particular restriction. N has to be greater than or equal to 2. Now note, they're not stating that I'm using the domains of the whole numbers or, integers, but don't use 2.1. You could 2, 3, 4, 5. Okay, because again, they're not telling us what is the actual domain this belongs to. Just use whole numbers unless they tell you to do something else. So if this is the first term, let's see what happens when I try to find the second term, A2. So here, this is the basic formula, and I'm going to try to find A2. I want to know the answer to A2. So A2 will be equal to A2 minus 1, because again, this n is exactly the same as this n. So I'm trying to find the second term, and I plug it into this formula. So now let's go ahead and work this a little bit. The second term is equal to A2 minus 1 is A1 plus 2 times 2 is 4 minus 1. Now, this is why A1 equals 1. It's important. Since it's the first value I'm plugging into my system, I know that this A1 is substituted for the value 1. And now I just add. 1 plus 4 is 5 minus 1. 1 plus 4 is 5 minus 1 is 4. Give me a second. Here in the book, they're telling me that A1 equals 1. And yet, okay, I want you guys to just visualize this a little bit. In the actual instruction, they're telling me A1 equals 1. But when you look at the bottom, it says, use the given term, A1 equals 2. So either we're going to use the 1 here, or let's actually change this for 2. So again, when you look at the book, realize that in the actual instruction, it tells you A1 equals 1, but in the actual problem under that, it says A1 equals 2. And the rest of the problem is done using A1 as 2. So that's a mistake in the book. Let's just use 2. You can confirm yourself. The number's different. Let's go for 2. So now, in order to find my second term, after I substitute my A1 for 2 here, I added it's 6 minus 1 is 5. So I have my second term, which is 5. What am I going to do now? I'm going to plug in my second term into my recursion to find the third term. Oh, I'm sorry. Let me not erase this. So now let's try to find, using recursion, the third term. A3 equals A3 minus 1 plus 2 times 3 minus 1. The third term is equal to 3 minus 1, 2. Again, here's where the recursion kicks in. Now I'm using a2 instead of the first term, a1, plus 6 minus 1. I know that a2 is 5. 5 plus 6 is 11, minus 1 is 10. So I know that my third term is 10. I'm going to plug that into my equation to find my fourth term. A to the fourth power equals a 4 minus 1 plus 2 to the 4 minus 1. Again, recursion kicks in. A3 is 10, so my fourth term is 10 plus 8, which is 18 minus 1. The fourth term equals 17. And that's pretty much it. Now give me a second. The second term is 5. The third term is 10, 17. And they're also asking me to find the fifth term. I was wondering, I just forgot how many terms they needed. They gave me the first one and they said find the following 4. So the fifth term, 5 minus 1 plus 2 times 5 minus 1. The fifth term is equal to a to the 4, which is 17, plus 10 minus 1, which is 27 minus 1, or 26. And again, this is just using recursion. You can see how, given the first one, I was able to find, using the formula, given the first one, I was able to plug that value in to find subsequent answers using recursion. So for the homework, all you have to do is, again, these aren't that difficult, 1 through 6, which is just looking, from the exercises 1 through 6, which is just looking at those patterns and writing the next 4. So it's kind of like a puzzle. And then 12 and 13. Again, you don't have to do this. Well, yeah, you kind of have to do it that many times, but it's going to help you practice. So this should take you maybe 15 minutes. If you have any questions, let me know. Otherwise, that's today's class. Please post the homework before 11 p.m. If you have any questions, let me know. You guys don't have class on Friday, so I'll probably give you guys the vector exam next Monday. So you have the weekend to, call me up if you have questions or to study without being pressured. So this week, we're going to have sequences in series and then just review over the weekend if you have any questions. Otherwise, have a great day. Have any questions, let me know. I'll see you all tomorrow. Take care.